In this section, we're going to talk about torque and rotational inertia as well as simple harmonic motion. Torque measures the ability of a force to rotate an object around some axis. It's going to cause angular acceleration, and the symbol we will use for torque is a symbol called tau, which for our purposes is just going to be a capital T. I try to write it a little curvy just to distinguish it from torque. So the symbol for torque is this T, and it's going to equal the force times the radius of the rotation. The unit I'm going to use for torque will be the combination of the units of the variables, which will be Newton meter. R is going to be the perpendicular distance from the axis of rotation, and the unit for the radius is going to be meters. If I have a seesaw and I want to balance two objects, then I'm going to take the force of the first object times the radius or the distance to the center of the rotation, and then I'm going to set that equal to the force of the second object times the radius to the center of the rotation. These two, F times R equal F times R, are going to be equal when the seesaw is balanced. So if we want the seesaw to be level, then F times R equals F times R. If I'm doing something like taking a lug nut off of a tire, then the tire iron or the wrench becomes the radius of the rotation as I'm either pushing it down or pulling it up and trying to remove or trying to tighten the nut on the tire. The crane here apparently, as it lifted the boom up for the arm of the crane, was not secured. Usually they will anchor these devices when they extend the boom or the arm of the crane so that they don't generate too much torque, which then resulted in the crane tipping over. The lever arm is the perpendicular distance along a line through which the force acts and the axis of rotation. So I'm pushing down on this tire iron. Here's the center of the rotation, and the lever arm is the tool's length. So torque is going to equal force times the length of the device there. And again, if we want to balance it, just like we talked about before, F times R will equal F times R in the case of a seesaw or something we want to have balance and to be level. Sally has a mass of 45 kilograms and is sitting 1.5 meters away from the pivot point of a seesaw. So R1 is going to equal to the center of the rotation 1.5 meters. We know that she has a mass of 45 kilograms. The second person is Jane. She has a mass of 55 kilograms. And so that's mass 2. And we're going to calculate how far away from the center of the rotation she will be. So we know that force of an object can be calculated by mass times, and when we're talking about F of G, which is what we are needing, is a weight measurement, we're going to take the mass and multiply by 9.8 because we're on Earth, and that's the acceleration due to gravity. So force of an object when we're given mass can be found by calculating and multiplying by 9.8. The math is going to be 45 times 9.8 times 1.5 will equal 55 times 9.8 times R. You will notice that 9.8 cancels. It's on both sides of the equation. I will want to talk about it here though, because if I'm just talking about torque, then it needs to be included in the calculation. So let me go ahead and just divide both sides by 55 times 9.8. 55 times 9.8, and all in parentheses. Make sure you don't make a math mistake there. And when we calculate the radius, we're going to get 1.23 meters for the second object, and logically that makes sense. The second object, because it has a bigger mass and bigger force exerted downward, needs to be closer to the center of the rotation. Final answer, 1.23 meters. Rotational inertia is the resistance of an object to changing its rotational state of motion. And rotational inertia depends on the distribution of mass of the object. If an object has more mass near the center of the rotation, it's going to have less rotational inertia, which means less resistance to change. So if I have a long stick and I put a big mass here on the end, and then I try to rotate it, when the mass is towards the edge of the stick, then this is going to be more difficult to rotate than if I put a big block here. So let's say I move this and I change it and I put something closer to the center. This object on this same stick is going to be easier to rotate. So an object with more mass further away from the center of rotation has more rotational inertia, more resistance to changing its motion in that circular path. So again, the resistance of an object to changes in its rotational motion is rotational inertia. Rotational inertia increases as you move the mass away from the axis of rotation. An example would be a baseball bat. If you have a long bat that's held near the end, it has less rotational speed than one that is choked up. So players are told to choke up if you want to get the speed of the bat going, because it's easier to change the rotation of the bat when you are holding it closer to the center, because it has less rotational inertia. People and animals with long legs are also examples of objects that have more rotational inertia. It's harder to get their long legs moving because of the length of their legs. So long legs have greater rotational inertia than short legs. So if the animal has long legs, they may have a slow walking stride. This doesn't mean they might not cover more distance with each stride. It's just talking about the frequency of their steps. An ice skater can spin around really fast by decreasing their rotational axis or decreasing their rotational inertia. And how do they do this? They're going to pull their arms in, and then they'll be able to increase their rotational speed. So by extending the arms out, you increase your rotational inertia, more mass is extended away from the center of the rotation, and the speed that you spin slows down. When you pull your arms in, your rotational inertia is decreasing, and then your rotational speed will increase. And we will demo this in class. And also, this is going to apply when you're doing flips in gymnastics and cheerleading. If somebody is doing a layout, so they are flipping with their body fully extended, they have a lot of rotational inertia. Their mass is extended away from the center of the rotation. And so this speed with which they turn is going to be slower than when they tuck. So when they tuck their legs in, their rotational inertia decreases and their rotational speed is going to increase. So here's a question. When is the rotational inertia greater for an Olympic gymnast? When he's swinging at full length. So there's a device they use that's a bar. And so if, let's say, this is the gymnast and his body is extended, and then he's spinning around this bar that he's hanging onto. And then he tucks in. So in the second example, he would be basically curled up into a smaller ball. And then he would also be spinning around at a faster rotational speed because his mass is more centered in the middle of the rotation. So rotational inertia for a skater would be when their arms are extended. So this is the highest rotational inertia here. But when the skater has their arms down at their side, then they have less rotational inertia, greater rotational speed. So they have more rotational inertia, slower rotational speed here. We're going to talk about periodic motion and specifically pendulums. Periodic motion is motion that repeats itself. So a yo-yo going up and down, a pendulum on a grandfather clock, and a mass on a spring would all be examples of things that go back and forth and their motion repeats over and over again. For periodic motion, the period is T, and that's the time needed to complete one full cycle of motion. So if I have this washer on a string and it goes back and then it comes to the center, it goes out, and then it comes back. The time it takes to go from here out and back again would be one cycle of motion or one period for this pendulum. The equation that we will use for a period, and this time capital T means the time. Do refer to your formula chart for more help. So 2 pi times the square root of, underneath the square root you have the length divided by the acceleration due to gravity. So in parentheses underneath the square root, the length of the pendulum in meters and the acceleration due to gravity, 9.8 meters per second squared. Frequency, we are going to use the symbol F for that, is the number of cycles per second. So cycles per second is one way to talk about the unit for frequency. Frequency can be calculated by taking 1 divided by the period. And let's do the opposite of that. Period is equal to 1 over the frequency. The unit for period is seconds per cycle. The unit for frequency is cycles per second. Amplitude is the maximum displacement from the equilibrium position. In our example of the washer on the string, this is the equilibrium position. So the center of the motion, and from that center, the washer is going to go out, come back, go out, come back, but it's always going through that equilibrium position. So amplitude is how far it is from the center. How far it is from the center. A pendulum has a length of 0.67 meters. So that's going to be the L in our equation. What is its period? We're solving for T. And so T is equal to 2 pi square root of the length, which is 0.67 meters. If it's not in meters, make sure you convert it, divided by 9.8. When the result is calculated, the period is going to equal 1.64 seconds. So make sure you're running through this and understanding how to use your calculator to get this result. What is the length of a pendulum with a period of 1 second? So we are solving for the length this time. We don't know it. We know the period is 1 second. And so this is going to require some algebra to solve. Let's write the equation first. 2 pi square root of L divided by G. I'm going to go ahead and enter the numerical values into this equation, and then I'm going to rearrange. So the period is 1 second times 2 pi equal times 2 pi square root of L divided by 9.8. I am going to divide both sides by 2 pi because I need to get L by itself on one side of the equation. So let me rewrite that. 1 over 2 pi equal square root of L divided by 9.8. To undo the square root, I'm going to square both sides. 1 over 2 pi squared. And then let me rewrite this. 1 over 2 pi squared equal L over 9.8. By squaring the square root, I get rid of the square root. And this needs to be in parentheses. I'm going to multiply both sides by 9.8. And that will give me my final answer. So the length is going to equal 0.248 meters. There will be more than one way to rearrange this. And of course, you can rearrange the variables before you put the numbers in as well. But do whatever makes sense to you. But the final answer you should get, no matter how you do it, is going to be 0.248 meters. Simple harmonic motion results when the restoring force varies linearly with the displacement. So as I increase the force with something that is in simple harmonic motion, the displacement of the object that's being acted on is going to increase. So if I have a spring that's attached to something, so let's say this is my spring, and I have a block on the end of it. If I extend the spring this distance, then I'm going to talk about the displacement here. But if I extend it further, my displacement increased there. My force is also going to have to increase. So it's just saying, as your force goes up for something that's in simple harmonic motion, the displacement of the object also goes up. So alternatively, if you decrease the force, then the displacement is going to decrease.